In this fourth lecture video on momentum and collisions, we're going to discuss conservation of momentum. The law of conservation of momentum states that the total momentum of a system remains constant when no outside forces act on a system of moving objects. In other words, as long as there aren't any outside forces acting on a system, the total momentum of that system remains constant. Let's take a conceptual look at conservation of momentum. Here we have an adult and a child on ice skates. The total momentum of the adult-child system is 0 since they are both initially at rest. Now, let's say the adult pushes the child. The child starts moving in one direction and the adult starts moving in the opposite direction. The child will travel at a faster velocity than the adult. The total momentum of the child-adult system is still going to be 0 because momentum is conserved. This is why the child with a smaller mass will travel faster than the adult with a larger mass. Let's take another conceptual look at conservation of momentum, this time using rockets. The total momentum of a rocket sitting on a launch pad is 0 since the rocket initially isn't moving. As the engines are fired and the rocket takes off, the sum total of the momentum of the rocket and all of the gas particles must still equal 0. If we are looking individually at each of the gas particles, the momentum of the gas particles is equal to the mass of each particle times its velocity. The total momentum of all of the gas particles is the sum total of each of the masses times velocities. Looking at the rocket, its momentum is the product of its mass times its velocity directed up. The momentum of the gas particles is directed down, so the total momentum of the system is the momentum of the rocket directed up and the momentum of all the gas particles directed down. Therefore, the total momentum of the rocket system will still be 0. The idea of conservation of momentum leads us to the impulse momentum theorem. If the mass of an object is constant, the delta p, or change in momentum, is equal to the mass times delta v, the change in velocity. This means that if mass is constant, a change in velocity will lead to a change in momentum. We also know that impulse is equal to the change in momentum from the previous video, so F, the force, times delta t, the change in time, is equal to delta p, or the change in momentum. Combining these two equations, we see that force times change in time is equal to change in momentum, which is equal to mass times change in velocity, or mass times final velocity, minus mass times initial velocity. A force applied over a certain time leads to a change in velocity and vice versa. This concludes our discussion of conservation of momentum and the impulse momentum theorem.